Hello and welcome, viewers, to another special episode of the Tutor Wizard live stream. We have more ancient history of math for you today. So, Adrian, take it away.
As I pound a Pepsi and then switch to coffee. Yeah!
Let's do it.
So we're going to do base B representation of numbers, and then we'll go through the kinds of numbers if I find a pen that works. There we go. So what we were talking about last time was the epiphany of the idea of number and the difference between one and many, and then needing a symbolization for this, and going through the journey of, at first when we thought of number, the first concept of number would have been a whole number, noticing that we have one thing, one pen or one coffee mug or one Pepsi and these types of things. So I have one and then we need a symbol for it. Over the years and through the cultures, a lot of people used a pebble for one or a line for one, etc. And then we finally get a symbol that is an altered one so that we have a unique symbol for it. I believe, or so the myth goes, I don't know if this is exactly true, but originally when they're doing these, that has one angle in it, so it was a good symbol. And then 2 has 2 angles in it. And then 3 has 3 angles. And then so that's a good idea. The number of angles represents the quantity in the symbol. But as we go, we're going to be, Pandora's box is going to be, you're always going to know about the representation of the numbers in Hindu Arabic. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those symbols are all you need to represent all numbers for all times. And then what we'll do is we'll go over this representation. This is called decimal notation or base 10. Decimal in Latin is base 10. And then in that scenario, what we can now do is focus, say, and notice also that those are the possible remainders when I divide by 10. It's got a squeak dividing by 10. I gotta find one of these pens that actually has juice in it. There we go. So from these symbols, we can create, what do they mean by base B representation or positional number systems? What we want to do is we want to have a way of describing every single number, but not invent new symbols every time we have to. So the clever idea with what Brahmagupta, I believe, and Aryabhata and Muhammad ibn Musa al-Khwarizmi are doing is they have the epiphany that if I just use a set that has these symbols in them and I call them decimal digits, actually that's where bit comes from. Bits are binary digits. And then what they took was the B. What is that, a portmanteau? Portmanteau! So bits are little bits, little bits. This made me think of the South Park one, or little bites. When they got the little bites, we got little bites. But we got, bits are going to be binary digits. And in binary, the remainders are just 0 and 1. So what they realized is in China and Leibniz, who helped derive calculus, realized you can describe all numbers in the entire universe with just on and off, zeros and ones. And so what does this positional system do, and what are we actually doing with this positional system? And then let's go through, usually I do, well, I guess we can do both right now. We're going to use these symbols that Pandora's box has already been opened, and discuss base B representation for any B greater than or equal to 2. But as we do that, we also want to develop the different kinds of numbers that we have. So the different kinds of numbers we have and we're going to get sets of them. And so I'll use a little bit of set theory notation, nothing too major. But if you don't understand something, you can make a comment in the chat, etc., and then we'll fill in the gaps. But we have sets of numbers. The first one is going to be the whole numbers, or the positive integers. And this one gets slightly different around, or you could call it the natural numbers. And I guess we'll just use n, which is going to be 1, 2, 3, the whole numbers that you count. And what's nice about that, close this bracket. What's nice about this is once I have the idea of these symbols and I explain what a base B representation is, or a positional system, that's why they call it positional, because what they're going to use is, now what we're going to use, notice that when I write that down too, 10 doesn't have its own symbol. 10 is these two symbols put together, which actually means, by definition, one group of 10 to the 1 plus 0 groups of 10 to the 0. This is the 10 spot and the 1 spot. So 10 even in itself doesn't have a positional system, but what we're going to do is we're going to look at powers of 10. And then what we're going to do is we can use these symbols to write them in a positional system, and then we don't have to invent new symbols. We can just use powers of 10, which can keep getting bigger and bigger, and then these 10 symbols, and we can write down every number that there ever has been. So even in this set, when it keeps going, all we're going to need to represent any of those numbers is those 10 symbols. Once we do that, we also start having commerce over the years. And I'm going to condense like 5,000 years of history of development of the numbers into like a few sentences quickly, and then I'll recapture them all when I ask you, how do you take all these sets of numbers and represent them in base B in decimal notation? So the next one we would have is the integers, Z, and what that's going to be is the myth of the negative numbers, -2, -1, and then 0, the epiphany that there's a representation of nothing, and then 2, 3, ellipsis. And then we get the integers. And then the next thing we are going to get is, this one comes from commerce and not sharing. I needed 5 apples, but I could only afford 2, so now I owe negative, or I owe, and so I have to use this symbol to, these two will combine to get back to give me 0 when you combine. That looks like I got a really creepy smiley face. Do you see it now? It's like, now I see it. So we got these symbols. Then what we're going to do is we're going to start sharing, and when we share, we get quotients of integers. And so this is going to be, now I'm using set builder notation, m over n, such that m is an integer. That's, so the fancy e means in. So this one is in this set, and then what I'm going to do is I'm going to let n be in this guy. And then that, cleverly, what that did is, this says Q is the ratio of all integers, where the numerator can be anything, -0 or positive, but n has to be a positive integer. And most importantly, what that does is, it does 2 things. It means you can put the negative in the top if you want. If you had 2 negatives, they're going to cancel. If you have 2 positives, there is no negative necessary. If this had a negative, for all intents and purposes, you could move it up, is what that's saying. And then so you can always put the negative on the numerator. And more importantly, you can't divide by 0. We'll get into that later. But this saying it's in here eliminates the possibility of it ever being 0, so you can't divide by 0. So this is the ratio of integers where the denominator is not 0. And then the last one we get, where we showed root 2 last time, is irrational, so that there are irrational numbers. They just use the complement of the rationals inside the reals. And so this is numbers r that are not equal to m over n, such that m and n are in Z. And now it didn't matter. Even if the numerator is 0, it doesn't matter. You can't have, these are numbers that are not the ratio of integers. And what they wanted was this, for this to be empty, the empty set. But it turns out that this is not empty, because root 2 is in there, pi is in there, e is in there, etc. Those are the 3 major ones. Think of a bunch more. Root 5 is in there. the fourth root of root 5, and those types of things are going to be irrational numbers that can't be written as the ratio of two integers. Also, what we're going to show is that what we can show is that the decimal notation or any of these base B representations will show us that I'll get into the fact that if you're in this set, the easiest way intuitively to think of the real numbers that I do instead of dealing with Dedekind, Kac, and Cauchy sequences and being fancy pants. For just us lay person or the mere mortals, what I want to view the real numbers as is, he says, the mere mortals, and he says the disjoint union of the rationals and irrationals. So what we want to do is write it like this. So what this is going to say is we have a real number. Every real number is equal to either a rational number, which has, we're going to find out, I won't prove it, but we'll write it down. It's in the notes and we'll reference it somehow. This has a repeating decimal expansion, or is what that one is. You are irrational and you have a non-repeating decimal expansion. So, and the disjoint part means that the bullet in the middle means disjoint, and disjoint means that the intersection of those two things is empty, i.e. you can't have a number that has both a repeating decimal expansion and a non-repeating decimal expansion at the same time. It has to be one or the other. And so what we have to do is look at the decimal system and then take the journey through, once we have the decimal system or any base B system, what does it look like and how do I represent numbers in that system with the decimal notation? So let's get into that. So these are the types of numbers. Well, then we have R, and then we can keep going, which is the ones that we have. There's a nice one, a Matryoshka doll. N is inside Z, which is inside Q, which is inside R, which is inside C, which is inside Hamiltonian, etc., etc. So this means contained inside. So this set is right there inside this one. All the numbers, if you put them over 1, all of the integers can be viewed as the ratio of two integers. So this one is inside that one. And then this is the one, that's why they called it the complement. There's the rational numbers. And here's the uncountably many irrational numbers. And this would be R. Every number is either a rational or an irrational, and you can't have a repeating expansion and a non-repeating expansion at the same time. And then all of these guys are inside here as a Matryoshka doll, or an egg with a bunch of smaller yolks. I don't know. Okay, so now what we want is to have a base B representation. What we're going to say is theorem. If we let 2b be at least 2 and have it in, n, we're going to put it, well, it doesn't matter, that one was okay. Well, we can't use the number 1 because 1 to the k is always 1 for any k, so we're not going to use that because they're not going to grow. The powers of them won't grow. However, if I use 2 or larger as my base, be the base for representation. And what we're going to use is the base B digits. So I'm couching the terminology in the theorem. Base B digits are going to be in the set 0. And notice that these base B digits are exactly the remainders when we divide by B. Other numbers by B. We haven't really talked about division, but I'm assuming you have K to 12 and we're starting a history of math class. So I'm abusing already the fact that you've learned something about math and you're not on square one. So this will be 1, 2, up to B minus 1. Notice that I did that exactly for the decimal notation. I did 0, 1, 2, and then 10 minus 1 is 9. So it looks slightly different when we use the abstract notation, but this is what they're talking about. This is the decimal notation specifically. So you take any base you want. In ours, we take 10 classically, but you can take base 2, which would be binary, or 3, which is trinary, et cetera, or ternary, whatever you want to call this. And then I take the digits. Now I don't have to create any more symbols. And then what the theorem is saying is then there its existence and uniqueness. There is a unique, so that means there won't be, so there is the first part of that couched statement, and then unique is the second half. So that there is what you would have to prove in the statement first, and then you would have to prove that there are no more. Oh no, don't do that. How did you do that? I've just gone into, stop that. Uh-oh.
What'd you do?
I've set my computer onto preview and it's showing everything on escape. There we go. Escape. I was like, it's the whole screen and I can't see the chat or anything anymore. I was like, help. So the there is means that you'd have to show that there is a base B representation for every number, and then the uniqueness, you'd have to show that there are no more. We're just going to use it as a statement. It's in my lecture notes, etc. We'll post a clip of it, and I'll give the history notes, and you can have this. Well, we'll have to figure out how we're going to parse that out, but we'll put the statement and the proof of it in the chat for later or something like this. Something. Get to it. Then there is a unique base B representation for any number, let's say n in R. So we're going to write n equals, and what are we going to do? Normally you write it as dk dot 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 d2 d1 d0, and then we would normally write that, but then what I'm going to do is cleverly write brackets to write it as a b to remind you that we're using powers of b, not powers of 10 always. And then what does this definition actually mean? The positional system, instead of writing to have to write the definition down, what we have is that this is the positional system. And what the positional system is, it's backwards because it was the Arabs doing this first. So from my point of view, it's backwards, but this is 10 to the 0, 10 to the 1, 10 to the 2, up to 10 to the k. So this is the shorthand notation for actually saying that this is dk, one of these digits, times 10, and in this case, see, my brain already does 10, but in this case now, because we're using base b, this will be b to the 0, b to the 1, b to the 2, up to b to the k. So we take powers of the base, and then we multiply them by the digits, the base b digits. So then this would be d2 times b squared. In our language, 10 squared is called 100, 10 cubed is called 1,000. And then this would be the d1 times the tens digit, or the b digit, and then the d0 is times b to the 0, which is a 1, and so they usually leave it off, and then that's your 1 spot. Then they call it the 1 spot because b to the 0 is 1. So every number has a base b representation, and there isn't more than one. It has a unique base b representation, and this is what the clever numeration system is doing for us. It allows us to compactly have a notation for every number we ever had, and I don't have to keep creating new symbols to do this. All I need is b of them, 0 to b minus 1. There's something on the board and I feel a sneeze coming on. I'm trying to avoid it. I'm trying to avoid a sneeze.
You're muted for the time being then. Let it out. Let it go. Sneeze it out.
Don't worry about it. Oh, maybe. We'll see. It's all right. Okay, so now what does that say? Now let's look at representing. Instead of proving the theorem, etc., let's look at each type of number. Each type of number with the base b equals 10, say. We could use any one you want, but I'll focus on representing numbers in decimal notation so you don't have to reinvent the wheel. Maybe next time I can go through the journey of representing them in... I don't think it's the Easter holidays. I don't know when Easter is. That's what I was saying. We had an Easter holiday yesterday.
Check. It's 2 more weeks from today.
It's on the 18th.
On the 18th. It's like, yeah, oh, I don't know when it is, but all I know is the family said there's a dinner yesterday and it had both turkey and ham, and I didn't have to cook, so I showed up. I didn't know what the holiday. I don't know. I don't ever know what the holidays are for, but I'll go to whatever you guys are celebrating and eat your food. So let's use base 10 representation, and then next time we can possibly get into doing all of the other base B representations and converting back and forth. But then this is where the history starts turning into, I just start clinging to the math and starting to want to do math computations. So I'm going to keep trying to tell the story of what's going in and be a history teacher for this one. Yeah, poke me back into place. So what we're going to do with this is we have the natural numbers or the whole numbers, then we have Z, then we have Q, then we have Q complement. And then we're going to do the same thing would happen when you do exponentiation. You want to do the same thing in your mind. So first of all, there's a journey 3 times sort of. The first time is just to develop the numbers and a symbolization for them all. But then now I have this clever representation. So what I want to do is then I want to talk about what these numbers look like in base 10 representation. But then eventually you want to ask yourself, when I do exponentiation, 2 to the n, this is higher order, and we'll get into that too. That's why BEDMAS works the way that it works. You can do BEMDAS. I'm going to do BEMDAS. That's a B. BEMDA. BEMDA. BEMDAS.
Do you want to take this question on the chat?
Okay, so yes, this would be Fibonacci in the 1200s. Brings it to Europe. He brings the Hindu Arabic symbolization of these symbols. He goes through the Silk Road, the same one as Marco. Nobody. Oh, I pointed, but nobody sees Polo. Oh, you can see in the camera, Marco Polo. So there's the Silk Road, and Fibonacci goes down this as well, and then he goes and he meets with all the Arabs in this, and in Baghdad in the House of Wisdom, they are fleshing this out entirely. Fibonacci gets his hands on these Hindu Arabic symbols and brings it to Europe in about 1200. Yeah.
Just looking at that date, that's quite lucky, because it was less than 60 years after that the Mongols burned it down.
Right. And it's also coincidentally nice as to, in the same vein of you asking this, why is it that what's the statistics on whether I pick 2 random countries in the world and they speak the same language? Slim to none. But if you take 2 random countries in the world right now and ask what kind of symbolization you use for your numbers, what are they going to use? Base 10. And why is this? Well, consolidatingly, probably that it funnels to that is because we have 10 digits on our bilateral symmetry body. We have 2 hands and each has 5 fingers, and 10 is 2 times 5. So that's probably going to be the push as to why we all like using it. It's also sort of a Goldilocks land of the symbolization. You'll see that it's just right. Base 2 is a little bit too much because the strings get really long. Base 60 is a little bit way too much because then you have too many, you have a 3600 multiplication table. So then this is a little bit crazy. And so base 10 is just right. So it's like a Goldilocks land also. But in there, I think... Now I forget what I was going to do.
The Goldilocks land of base 10
so the base 2 is too much, base 60, and then base 10 funnels it in there. And the Roman numerals, you have to keep creating base 60s. Well, yeah, the Akkadians, it's Babylon. which is not, there wasn't just the Babylonians. More importantly, it would be Mesopotamia, which had the Akkadians and a bunch of the other ones in there as well. But the land between two rivers, Mesopotamia, is in the Fertile Valley, is where this is all starting originally. And then it's Fibonacci brings it back to Europe and then tries to reform the rest of Europe into this, which he does fairly successfully. Oh, and BEMDAS, the order, was the other thing that I was trying to remember. So what we'll also do is, why is this working? It's everything is addition. Subtraction is addition, and that's why they're at the bottom. So that's lowest order addition. Multiplication is and division are actually addition, but they're higher order. And then exponentiation is the point that I wanted, is the most highest order addition, and that's why you do the highest order first, then these two, then those two. So in this 2 to the n, say if n was a 2, what that means is the symbol means you multiply yourself by that 2 times. But what we're going to have to do eventually when we look at exponentiation in these weird ones, what does it mean to multiply yourself 2 by itself pi times? And so we're going to have to get into that and think about how to compute that thing in the different powers of the different kinds of numbers in here. What does it mean to multiply yourself by 314 over 100, etc., etc.? So these are the types of things we're going to have to get into later when we talk about exponentiation of weird numbers. But right now, in the powers that we're using, we're assuming that the powers of our base b are just integers, so we know what that means. The 10 to the k means you multiply 10 by itself k times. And so then there's nothing that we have to worry about right now for this weird symbolization. Okay. So now what was I doing? So now what we want to do is represent numbers. Just wait, I am going to sneeze.
You're muted. Sneeze away. Sneeze away. All right. 2 to the n is different from... So, just for our... No, I gotcha. So just for our friend here, Sensation Black, 2 to the n... Oh. Why, thank you. Is that better? Oh, yeah, okay, there you go. And I try not to pick up so much ambient noise here with this microphone because it's actually really good, really sensitive. But, oh, okay, Adrian's back, so if he wants to get the question then.
We got another question? No, it's the same thing. 2 to the n is equal to 2 to the n. That's going to be okay. And then again, when we get into this, we would have to start talking about, also, I'm assuming this is why, so you're asking fairly good questions, but b is larger than 2 and it's a positive integer, so I can't take anything negative in there. But once I start putting this negative myth in there for negative numbers, then you might want to start using the brackets also. I didn't have to do that, but it was a good noise. But
I was just going to say, you probably want to see a doctor about that.
So if I had negative 2 to the n, that would not be the same thing as negative 2 to the n. And then they're going to start using, and then that's also the BEMDAS. When we want to start, now my brain says BEMDAS every time. In BEDMAS, or this acronym of the highest order, brackets are just used to clarify notation and simplify things, like in associativity, etc., etc. And then you do highest order exponentiation to lowest order. So this would be, the negative would be technically on the outside, so you would compute 2 to the n. So if this n was a 3, this one would be negative 8, but this one also would be negative 8. But then if I switch it to a 4, this one would be negative 16, and then this one would be negative 2 multiplied by itself, negative 2 times negative 2 times negative 2 times negative 2, 4 times, and that would be 16, and those aren't equal. So then, yes, you have to worry about the brackets when you have a negative in there. But for positive numbers, we say BODAS. Okay, yeah. BODMAS. Yeah. We'll explain that all, but it's not going to be today. Let me not fall off the train tracks and keep this going. So in the first one, what we're going to do is in n, how do we get the decimal notation for them? Well, all we have to do is, if I want 123, well, then I would have to say that that's, when I say it, it's 100. And then in German, I like it better, 3 and 20. 23. They would say 3 and 20, they say. And we've shortened it to say 123. In the German, it's backwards a little bit, because then that's why I say they say it. But in the German, it's the remnants of them doing it the correct order, because we would write 23, but we should be writing it as 3-2, because it should be the 1s 10 to the 0 here and 10 to the 1 here. But we've been trained by Al-Khawarizmi to write it the other way, that we would have 10 to the 0 here and 10 to the 1. I just hurt everybody's brain probably, but we're not going to do that. It's not 32, but it should be it should be 3 and 20, because in English I want to write it that way, and in the Arabic I want to write it this way. But 23. That was really hard. I said it in German, then wrote it in English. My brain hurt for a second. So 123, there it is phonetically. And then when I want to write this into symbols, that says I have one group, 100 men, 10 squared. And then I have 20, means actually 2 times 10. So then what we're going to use is a plus. And then we have 2 times 10. And then plus, we're going to have a 3 times a 10 to the 0. So we have one group of 10 squared, 100, 2 groups of 20, and then 3 ones. And so how we're going to write that symbol nicely is we're going to write it as 1, 2, 3. And if we're in base 10, what that means is exactly what I just wrote. This symbolization, if you want to write it backwards for yourself, that's 10 to the 0, 10 to the 1, 10 to the squared. And so that means that it's going to be 1 times 10 squared plus 2 times 10 plus 3 times 10 to the 0. And that is the decimal notation. So for whole numbers, that was the whole reason why they came up with the positional system. I no longer need to write out a whole bunch of new symbols like in Roman. All I need is 0 to 9. And now, no matter how big the number gets, I get the numbers, and I keep up with that with powers of 10 will get larger and larger. Now, in the integers, the only one we have to worry about is 0, but 0 you can write as many zeros as you want, so he's just his own symbol, but he can just be writing as an infinite string of zeros if you want, because that's just going to be 0 times 10 to the k plus 0 times 10 to the 0, but those are all going to be zeros, so it's okay. So 0 is, we'll get into the notation in a second, 0.0 repeating, which means he just has an infinite amount of repeating decimals. The other one is you have negative numbers in there, but if I want to know what negative 1, 2, 3 is, you can just throw the negative on the outside of the number. There we go. And that's what you were talking about with the brackets too. Now what I want to do is finally use long division, and it's these two that I want to know. How do I use my symbolization for our specific numbers? You drink coffee, and then you think about it for a second. I want to write m over n. So now he's going to have 2 avatars. We have the fractional avatar. But that means something. 2/3 cups. If I say 0.66 cups to my grandma, she's like, I don't know what you're talking about, but it's the same thing. So then we want to have our repeating decimal. And so first of all, let's couch in basically an example. I'll do a baby example. The theorem that says every rational number can have an infinite repeating expansion. So how do we get the repeating decimal from this? And so what we want to have is we want to have a D0, ones digit, or some kind of number where we have DK. And then now there's going to be some kind of decimal point, and then I'm going to need, what am I going to use, C1, C2, up this way, and then we're going to write the number like this, so we're going to need a new notation. So the first thing we notice with the rational numbers, the number might not be a whole number anymore, so we're going to need this decimal point. What's the decimal point really doing? The decimal point is important because this is where the powers of 10 become negative, or your base, whichever base you're using, become negative. So what these decimals mean is the second part is this will be C1 times 10 to the negative 1, which is equal to C1 over 10 plus C2 times 10 to the negative 2, which is C2 over 100. And so what the decimal point is saying is I'm still using powers of 10, but now I've used negative powers of 10. And coincidentally, that's how you define the exponents, or b to the negative n. If n is an integer, positive integer, this is written as the reciprocal of b to the n. So that's how we define exponents of negative integers. So that's what the decimal point is going to start needing in our journey. Once I do that, now let's look at, that's the extra notation we're going to need, and then let's find out how we actually represent them that way. So we have another theorem and another pen, hopefully. Theorem. No, that one's not going to do it. Oh, now I'm losing them. I want that orange one. So let R be a real number. R is rational, i.e. in this one, if and only if R has repeating decimal. And so what that's talking about is the two avatars. R rational means it can be written as m over n. That one's not working either. And this one means you're going to have a repeating decimal expansion. So instead of proving the theorem, let's do that with one of my favorite numbers, 2/3, only because I can write it as 0.666 repeating or 0.6 repeating, and the bar just means it repeats indefinitely. So the ellipsis and the bar mean the same thing, infinite amount of sixes. So this is the fractional avatar and this is a decimal avatar, but it's the same number. It's representing the same thing. How do we go? We'll go back and forth. So in the theorem, if you have a rational number, m over n, let's call it 3 or 2 over 3. If we have that fractional avatar, what I'm going to use is long division. And I'm going to use the first, there's a little bit of cheating in here too, but what I'm going to do is I'm going to write 2 and then I'm going to write a bunch of zeros down behind it and using the decimal point. I know this is going to be a number less than 1, so there's going to be 0 in my 1 spot. Also, you should write out the multiples of 3, etc. before you start. Times 1, times 2, times 3, times 4, times 5, times 6. That's all. I knew that's all I needed, but keep going up to 9. You only need a couple more. And then I'm dividing 3 into 2. This goes in 0 times. I get 0. I subtract. I get a 2 again. I bring a 0 down. 3 goes into 20. How many times? 6 times. And I get 18. I subtract. I get a 2 again. So then I bring another 0 down, and then it repeated, so you're just going to keep getting 6s all the way down. So what that says is 2/3 is 0.6 repeating indefinitely. So now I have the other avatar. But if I'm going to do that in reverse, I just showed you. Now let's do it in reverse. Do you know the clever trick? This is the part where I always get excited because they show one direction, but then I've seen these guys because I just finished teaching the class again. If I do this, they don't know how to go back. I just gave you that. How do I go from the repeating decimal avatar back to the 2/3?
In your class, when you showed us this, it blew my freaking mind.
All right, so let's do that. When I do this, we're going to use one-by-one linear systems, and we're going to use a clever trick. What I want to do is, and this is the power of Muhammad ibn Musa al-Khwarizmi, he calls it something. X, he says, let X be 0.6 repeating, which means that this is 0.666, and there's just 6s that just keep going. And this is now going to be the Hilbert Hotel is the clever move. That's why it blows your mind. It's the same concept. There's so many 6s, we'll just move one of the 6s down. There'll still be infinitely many 6s. So when I multiply both sides of this by 10, So now I can manipulate it. I'm going to call it 10x is equal to 10 times this thing. And when I'm cheating again, that's the little cheating I'm doing. But when I multiply this by 10, what is it going to do? It's going to move. Oh, maybe I should show it and not cheat. What this means is this is 0 times 10 to the 0 plus 6 over 10 plus 6 over 100, dot, dot, dot. And then I'm going to multiply it by 10. So what is it going to do? It's going to put a 10 into each spot. So then it's going to move it to 6 times 10 to the 0 plus 6 over 10 plus 6 over 100. And so what did it do? It moved the decimal point 1 in that infinite distribution. So when I multiply the 10 on this side, it's going to move the decimal spot, which will give me 6.6 repeating. And the clever idea is to create two numbers that have the same repeating part now. So now when I line this up, this is 6.6 repeating, and this x was just 0.6 repeating, and now I have two numbers that have the same repeating part, so I can subtract, and all of those things will go away. And now last time I checked, 10 minus 1 was 9, and then this is going to equal 6 minus 0 is 6. Now I have a 1 by 1 linear system, and x9 is not 0, so I can invert it, and this is 6 over 9, which is 2 times 3 over 3 times 3, which is, in lowest terms, 2/3. So the moral of the story is, from your number, create two numbers, either the number itself or two other numbers that have the same repeating part, and then you subtract them to get rid of all the infinite repeating parts, and then you can solve for the number. And this is how we get that essentially every number that has a repeating decimal expansion can be put into fractional form, and every number that has a fractional form via long division can be put into a repeating decimal expansion. And that's what we're doing. All right. I need more pens. Pause for a second. I gotta go get more pens upstairs.
So we're live, so there won't be a pausing here, but we can take over the discussion. So yeah, when I saw that calculation in his class back in History of Math years ago, my goodness, that opened up whole new doors for me.
Well, you know, a lot of times back in the day, oh, it's repeating 9, so it's not quite 1. Well, sometimes it is 1. Because it has to be.
Yeah, it goes on forever.
Yeah.
And then when you do that same calculation, you get 9 over 9, which is 1.
Of course, now, a true analyst would say, but what if we subtract epsilon?
Yeah, are you doing that one? Which is true.
Yeah, chat, join in.
Yeah. The chat joined in. Is that the one you're talking about?
Yeah, we're trying to encourage the chat to join in with that one, because that's a good one. That's a classic right there. And
you get the connection between this thing and power series representation, because that 0.9 is repeating it eventually. Be careful with the number when it's in base B. Folkerunda said, be careful of a number that has an infinite number of B minus 1s. Because in the power series representation of that, if I'm going to do that, what is that? That's 9 times 10 to the negative 1 plus 9 times 10 to the negative 2, which is equal to 9 times the sum from n equals 1 to infinity of 1 over 10 to the k. And so now I have a convergent geometric series. So you can view it that way, and then you can check this is a geometric series. 1 over 10 is less than 1, so it converges. And if you compute that thing, you can find out that you'll get exactly 1 over 9, and so 9 over 9 will cancel to give you 1. If you also want to do the dirty trick here, did everybody play?
I think that's the curriculum in Britain, right? Is that right?
Yeah. I was just reading his comments too. Yeah. Yeah, this is fairly universal. This is why it's everywhere, the base 10 representation. All right. Should we do one, now that we're talking about it and we're doing that and we've got everybody on a roll, let's do one more where it's not one of the obvious numbers, and I'll show you. Which one did I do? 1, no, yeah, this one, 2, 3, 1. Repeating, and the bar's only on the 3, 1. So what this number means is it's 0.231313131 indefinitely, not 231, 231, 231. So how do I convert this one into a fraction? What we're going to do is this one now, if you notice in the caveat here, the repeating part is not right next to the decimal like it was in 0.6 repeating. So I can't use this. I'm still going to call it x cleverly, but I can't use x specifically in my cancellation process. So I have to take this number and create two other numbers from x that have the same repeating part. If I move it once, multiplying by 10, I can get the 3131 right next to the decimal place. And then if I move it 3 times, I can also have a number and then the repeating part over and over again. So what I see is I could do 1000x would give me 231.31 repeating. And if I multiply by 10x, this will give me 2.31 repeating. And now we're in the same business. We can subtract. So I get 990. X is equal to, what do I get now? 229. Is that a prime number? 9, 10, 11, 12, 13. It could be. I'm not going to put it in lowest terms. I won't make you do it either. I'm pretty sure 229 is a prime.
Full marks for this one. Full marks for that.
You can have a cookie if you put it in lowest terms. So there, that's the clever trick. So the dirty trick is, what do? You call your number x, and then from x you create two numbers that have the same repeating part. Then you subtract them so that that all goes away, and then you can solve the one-by-one linear system for the value that you need. Good. Now we have to do the hot mess of, so now what that says is, hopefully intuitively I showed you, and then what you do with that intuition is you can just do the generalization and you write it for a general number n and a general number fraction, and then you show that they always, if you have a fraction, it can be written as a repeating decimal expansion. If you have a repeating decimal expansion, you can turn it into a fractional form. So long story short, you're rational if and only if you have a repeating decimal expansion. So now what they ask is, do we have numbers that are infinite non-repeating decimal expansions? And so the first clever one is by Liouville, who did a bunch in complex variables as well. But he takes this number and then he creates a number x from it by squeezing in one more 1 in between each 0. And so as you go out, there's more and more 1s always. So this can't ever repeat. So this has to be a non-repeating decimal expansion. So this number is not, there's a little bit more work there, but I'm waving a hand at it. But this number is one of the first ones that has been shown by our species not to be rational. We also last time showed that root 2 is not rational. So there are numbers that are in here. This is not empty, and we do need to flesh out the real numbers from this. And now we ask ourselves, how do we find the decimal expansion of pi, which is irrational, without our calculator? How does your calculator know that this is approximately equal to 3.1415? It's right above me. 9, 2, 6, 5. I'm good at this. 3, 5, 8, 9, 7, 9. Oh, it's like I ran out. Just wait. Where's the roll of the rest of the decimal expansion? There's a lot of the digits. We got more digits, but they should go all the way around the room one of these days. But how does your calculator know this? And also that's coincidentally how we're going to do 2 to the pi is approximately equal to 2 to the 314 is 314 over 100, which is 2 to the 314 to the 100th root. And that's how we're going to approximately, that's how your calculator is doing it. But how did it know originally that it was 3.1415? That one's a different game, but we're going to use power series representation. Arctan of 1 is pi over 4 is the hint, and then we'll talk about that later. So pi is 4 times arctan of 1. And then if you can find a power series representation, power series means that you're going to have a bunch of rational numbers in this. And so this is an infinite sum of rational numbers times 4, and then you can get at pi that way. It converges fairly slowly, but that's the first way of doing it. Let's step that back and do the Babylonian method of approximating square root of 2. I did that last time too, didn't I?
Yep.
Should we do root 5 then and see if I can do I had the powers wrong last time. Yeah, so let's do this one. How do we know the square root of 2? We use the clever Babylonian method, and then what you have to ask yourself is, how am I going to get the decimal expansion of these? Basically, it's called successive approximation via rational, excessive rational approximation. So what we do to compute, once we've convinced ourselves that a number is irrational, what we want to do is somehow use and get, in theory somewhere, a way of computing this number as an approximate amount of rational numbers, and then use long division to find the decimal expansion of that rational number, which is approximately this guy. So how do I do that? I draw a number line, and first of all, I know that 4 is less than 5 is less than 9. That's my first approximation in the Babylonian method, or the Akkadians. I'm not sure exactly which one it is, the Mesopotamians. Then I square, this is my first guess, so I square root, and that says 2 is less than root 5 is less than 3. What that so there's my 2 integers that it's between. It's going to be over here somewhere, probably. That's even probably too much. 1, 2, 3, 4. Those are all even, because I said. It's going to be right around here is where it lies. I know that because I already know the decimal expansion. But what that says already, we already got from our first guess what happened last time. Do you remember? That says we're already approximately 2 point something. And now we have to find the decimal digits. It's going to be 2, 3. But how do we find those digits? Let's try it. So our first guess is that we're between 2 and 3 from that square root business. Now what the Babylonian method is going to do is successively try to get us closer to that. And what we're going to do with that is I'm going to say, let's redraw that. I have 2 and 3. And I'm going to take the average, or the midpoint, and that's going to be 2 plus 3 over 2, which is going to be 5 over 2, which is 2.5. So now what I'm going to do is I'm going to let x1 equal that average. That's x, so this was x0 and this was y0. My first guess is x0 plus y0 over 2, the average or the midpoint of the first one. And what we're always guessing is that x1, y1 will approximately equal to 5, or we'll just cheat and say equals 5. And so the y1 is for free. It's just 5 over x1. And this is the Babylonian method. Every time, just switch the 1 to a k, and this is what we're going to iterate every time. So what did this one become? x1 was 5 over 2, and then now this one is going to be what? This is going to turn us into a 2 again. y1 is equal to 5 over 2, which is equal to 5 over 1 times 2 over 5. Cancel, cancel, which is 2. What did that do? That just switched me, but now what I have is, now our number root 5 is between 2.5 and 2 is what we just found. So it's somewhere in here. And then I reiterate again, x2 is going to be x1 plus y1 over 2, and y2 is going to be 5 over x1, or x2, sorry. Once I have that, what is this? This was 5 over 2 plus 2 over 1 over 2, which is 1/2 times, what are we going to do? 5 over 5, 2. Did I do that right?
2 over 2 instead of 5 over 5?
Yeah. I was like, where did I eat it? Wait. Yeah. Like, yeah. I threw myself off the 1. I just need 2 over 2. I was like, something's wrong there. My brain wrote something down wrong. That's right, right? 9 over 2. Yeah, there we go. 9 over 4. Thank you, disembodied voice. I can't tell whether it's external or internal. And now what is that guy? Can you take that guy? Let's take it, and I'm going to use the long division in the quotients for one I already know. 9 is 8 plus 1 over 4. And 8 has what? 2 and 1/4, so that's 2.25 in the decimal expansion. I'm already cheating and writing that up.
That was a question just now if we use the long division with this, but yes.
Yes, we're going to do it at the end. In each one, we can keep doing that. I was going to do one more, and then that's the guess that I screwed up last time. But let's do y2 is going to be equal to what? These numbers are going to get out of hand real fast. You're going to see in this step. Next step, y5 is x2, which would be 9 over 4, which is going to be 5 over 1 times 4 over 9, which is 20 over 9. So let's keep those ones, 20 over 9 and 9 over 4. So now we have to do it one more time. One more time, and we can get, what was that? X3 is going to be the average again, x2 plus y2 over 2, which is now going to be 20 over 9. And you'll see why I multiply by the 1/2. Divided by 2 is the same thing as multiplying by 1/2 plus 9 over 4. Let's do this right this time. I want 9 over 9 and 4 over 4, which is going to give me 1/2 times 80 plus 81 over 36. And then I'm not doing any more after this, because what did that give me? 161 over 72 is x3. And then in the next one, you can see we'll be in the thousands or tens of thousands. And then this is going to get a hand real fast. We'll use the computer. Thank you, Alan Turing. And then we'll use y3, which is 5 over x3, which is 5 over 1 times 72 over 161. What's 72 times 5? That's one of the Mayan calendars. 360 over 161. And then they had 5 unnamed days. And so let's compute there. Now, yes, that's the comment, right? This was y3. And now let's do this correctly. I should have done it correctly with the last one. Now I have to use 72 and 161. All right. Now I have to divide 360 and 161 versus 161 over 72. I claim that one of these is an overestimate and one of them is an underestimate to the actual value of the square root of 5 is what I'm trying to do. Where'd you go? Old man noise. I just made an old man noise. Let's do this carefully. Luckily, I know it's 2.23, so I'm only not going higher than 3. So 72 plus 72 is 144. Check, I got that one. I'm saying it out loud really slowly because this is where I'm going to start making mistakes, adding and multiplying small numbers. 72, again, is going to give us 6, 1, 2, 16. And then 72 again is going to give me 8, 8, 2, 88 times 4, etc. So now when I want to do 360, and then we're going to do 2 decimal places, say, but I'll show you what's going to happen here. And then we're going to do 161. Also, you can use, this is not mutually exclusive. I already know from the very first guess what should this first answer be. It should be a 2, because it told us that it was going to be approximately 2 something, and it exactly is. Am I doing that right? No, I'm doing the wrong numbers now. That's the 72. I was like, wow, I picked the wrong number. I should have done the 72 one, but let's write these ones out too. 161 plus 161. It's like, what happened there? 2, 12, 322. And then 161, I'm going to get 3, 8, 4, 83. And now you can see how many times does 161 go into 360? The times 3 was too much, so it had to be a 2 there. That's what's happening. And I already have the outcome, 322. I subtract. Now we can do the borrowing, etc. So I'm going to borrow from the 6, and I get a 10, I get an 8, and then I have 3. And then I bring this down, I get 380. I ask myself again, how many times does 161 go into this? it has to be, this is too much, so it has to be a 2 again. And I get 322. I borrow again, I get a 70, I get a 10, I get an 8, I get a 5. Those are going to cancel. I'm subtracting every time. And I get this guy. Oh, and then guess what? If I put it in there, what's that going to be? Did I do that right? That doesn't seem, yeah, it doesn't matter. I don't need it. This one was too much, so I get a 3. And then I'm going to stop. So approximately, I think it's 2.23. Now let's do the other one. I now have to do 161.00 blah, blah, blah into, I'm dividing 72 into this. Again, it should be the same thing, 72. Now it's the correct ones. Let's get rid of these so I don't confuse myself. 72 goes into 161 2 times, which will be 144. I can borrow 5, 1, 11 is 17. I'm going to bring a 0 down. 216 is still too much, so it's going to be a 2 again. I'm going to get 144. 6, borrow, 10, 6. I have to borrow because I can't do it in my head. I'm doing this. I stick to your guns. It's 26. Oh, and then what are we getting? 260. Yeah, 260. And then I can stick to it when I'm going to have a live audience. This is too much, and then we get a 3. I should have done one more, but you'll see that these numbers will be different now, and that's how you know in the check I'm going to be lazy because we're going to end right pretty soon because that should be good enough.
Yeah, we're already over an hour.
I know, it's time flies when you're having fun. And so that's how you know in this assessment. It's not the nth step will give you n decimal digits in this algorithm. What's happening is you take your two numbers. Okay, now maybe I just lost them, so I don't know what the number was. What was it, 483?
I think so, 43 and 6, well, 161 plus that. Yeah.
So, yeah, this one, if I do it one more time, I'm not going to do it. I'll screw it up. Now that I've done that with my...
2.2.
Yeah. Whatever these digits are, they're not the same. Let's pretend it's a 7 and a 5, right? Now that tells you, if it was a 7 and a 5, what that tells you is that this digit, and this digit are correct. And then you'd have to keep going if you wanted the third decimal place. So what that says is correct to 2 decimal places because I got them to match. Those aren't the right numbers, but I got them to match. That says that this is approximately equal to 2.23. And that one specifically is useful because the golden ratio phi is 1 plus root 5 over 2, which I can now approximately equal 1.618, et cetera, So we can get at the decimal expansion of these other numbers, which are irrational. There's another irrational number for you. And this is the base representation. So this is why they called them irrational, and they changed the name and everything. Some of them have infinite non-repeating decimal expansions, and I've trained my brain to start not doing the lie that your calculator says. It can never equal 2.23. It's approximately equal to 2.3, correct to 2 decimal places. That's what the square root of 5 is, because it's irrational, so it has an infinite non-repeating decimal expansion. That's a fairly good place to end. Oh, I hit the ceiling.
Thank you for joining us, everyone.
See you next time.
We will continue the journey through ancient history of math next week. But be sure to join us later this week for more of Tim's stats videos, and we'll have some other ones. Oh, a really quick question there. If you round it to 2
decimal places, does it not round to 2.24?
Yeah, we're trying to avoid decimal place. We're trying to avoid rounding by approximate.
So yes. Yeah. Okay.
Okay. So Adrian,
do you want to
finish
finish?
You go right ahead.
I don't want to approximate the numbers. I'm not approximating them. So yes, this is a very good question. Let me phrase this correctly. What they said as approximating and rounding means that they already knew your calculator already knew what the correct actual digits were in that expansion, 2.23, etc. And then yes, if you're going to round, then you'll spill it up or you'll spill it down based on whether it's 0 to 4 you round down and 5 to 10 you round, or 5 to 9 you round up. But I'm not trying to round the number to approximate. What I'm trying to say is I'm trying to actually find maybe I should rephrase the question so that this takes away the confusion. I'm trying to find the correct decimal digits for the square root of 5. And correct to 2 places, the actual digits in its expansion are 2.23 and then a bunch more. So then yes, if there was a 7 up there, it's not a 7 or a 5, wouldn't I round it? But this is not what I'm interested in doing. I'm not trying to say, oh, it's 2.24. That's lost the whole point. What I'm trying to do is I want that to be the actual digit that would be there in its expansion. Just like, yes, the chair at McEwen a long time ago, David McLaughlin said the same thing because we were talking about Pi Day. And in 2015, 31415 was a clever one. And he said, well, if you're rounding, technically it goes to 3.16. Pi is closer to 3.16 than 19. And I said the exact same conversation. I'm not trying to round. If I was going to round this, I wouldn't round up to 6. I want to know that that's the actual digit in the decimal expansion, so I want to leave it as the 5 even though it's the 9. So I'm not going to round. I'm not interested in approximating it that way, even if it was a 7. I don't think it is a 7. I think it's a 0 or something next. So you'd round down anyways.
So you're practically just cutting the tail.
But in this, yes, I'm approximating it by saying correct to the digits. I'm throwing away the rest of the expansion. I'm no longer doing what they foolishly did in K to 12. It's a 6. Yeah, 2.236. It's really easy to do when you got your calculator. Yeah, I got one of those too.
Hold on for a minute here.
Yeah.
There's an ad, so you keep
Yeah, I'll calculate. It's like, I don't know how to use the damn calculator. 5. How do I use it? It's like literally, it's like shit. I don't know. There it is. Equals.
Well, we have a comment about how that's fascinating, and yeah, it really is. People are enjoying the journey so far. This is what we want.
Yeah, Jazz U though in 1998, I just made up the 5 and the 7 because I didn't keep computing. You'd have to actually run the algorithm and do this. But yeah, it's 606. And so now that you have that and you're asking, I'm not interested in approximating the way that they train you in school, because in school they had no idea how to come up with this. They've used the calculator to rely on the fact that these are the correct digits, and then they're saying approximate it, and then they would have a rule. If I was going to cut it here, they would say you would round down because that's a 0, so you could leave the 6 is what you're saying and throw away that. But now if I was going to cut it right here and truncate, you're saying I would round it to a 4, but I would not do that in this problem because I'm trying to find the correct decimal digits of the expansion. And then you can play the game of rounding when it costs, when my coffee at Tim Hortons, which we're not going to do anymore. Who are we promoting now? This one?
Just the good ones, not the garbage stuff.
The game that you're playing is the digital coffee actually costs 47 cents, but it's actually 45 cents, so they round it down to the nearest 5s. They're rounding it down to the nearest nickel because they don't have pennies, which is also an interesting game because they used to have the 1 and the penny, but now they have the 5. So now they're playing the same rounding game. And if it's a 1 or a 2, you round it down to the 5. If it was this, you would have to round it to 50 cents here. I don't know if that's the same in all the countries in Britain and all these ones.
Australia got rid of their penny too.
They got rid of the penny, so then that's the same rounding game. So that's the rounding game I play every time she says at the counter, but then I pay cash because I'm a peasant. So she says 247, and they think that they can steal that 2 cents digitally, but I'm like, nay, Kilowa, I'm going to pay you 245 because I'm going to round down. I agree with that one wholeheartedly. Yeah, but when I'm trying to actually find the correct decimal expansion of pi or some irrational number, stop rounding them the way they would in school. I want the correct digits. Thanks for the good question. Keep them coming.
Neat. Yeah, in Finland, they no longer had the penny, so they couldn't use the 1 cent euro penny. What is it even called? A euro penny? Can I call it a euro penny? I don't even know.
Euro cent.
Euro cent? Yeah.
Yenny. It's a yenny.
It's a yenny. All right. Thank you for your great questions, viewers. This has been awesome. So we'll see you next time, but stay tuned for later this week. We'll have more stats with Tim and lots of other videos as well. More integrals. We'll continue our journey to 10,500 integrals later this week. We're just making up numbers now. Just keep going, Adrian. You're done when I say you're done.
Any integer, yeah. They keep going. There's infinitely many of them.
All right. Goodbye, everybody.
Yeah.